So today we're going to be doing a full run through of Chem 100 Laboratory 8, which focuses on calorimetry, specific heat, and the energy in foods. So first and foremost, all of the materials for this laboratory activity are found in the Laboratory 8 module. One thing I'd like to draw your attention to first and foremost is the brief introductory page, which talks about the learning objectives and some recommended reading for this chapter laboratory. The next thing I'd like to draw your attention to are the Laboratory 8 procedure and report sheets. These are available in Word and PDF file formats, and you're going to want to download or print out these procedure and report sheet pages as we'll be filling them in as part of completing this lab report. The next thing I'd like to draw your attention to is the Laboratory 8 Canvas page titled Laboratory 8 Calorimetry, Specific Heat, and Energy in Foods. This lab page contains a lot of useful background information in the introduction section. I would encourage you to read the introduction section in order to become familiar with the background for today's laboratory. In addition, this laboratory page also has all of the videos and photos that we'll be viewing in order to collect data and observations necessary to complete the lab report. So please make sure you have the Laboratory 8 lab page open as we work through this laboratory activity. Beyond the lab page, there's also a pre-lab lecture, which provides some background information on the calculations and theory for this laboratory. And this recording, which discusses and goes through the laboratory in detail, is found in the Laboratory 8 Lab Walkthrough video page titled Experiment 8 Laboratory Recordings, Video Walkthrough to Complete the Experiment 8 Virtual Laboratory. That's the video that you're viewing now. Finally, when we completely filled out our report sheets and we finished our report, you'll be submitting it to the Laboratory 8 report submission page titled Laboratory 8 Report, Calorimetry, Specific Heat, and Energy in Foods. With that introduction established, let's talk a little bit about the lab. So here are the procedure and report sheets. As always, we have a pre-lab checklist where we have to open the lab page, read the background reading and introduction section. I would encourage you to do that on your own time. You're going to want to watch the pre-lab lecture. And if you just have the procedure and report sheets handy, you'll want to open up the laboratory page titled Experiment 8 Laboratory Recordings, Video Walkthrough to Complete the Experiment 8 Virtual Laboratory. That's the video that you're watching right now. If you're asked to view a video or photo in Canvas, all the videos for this experiment are found in the Canvas page for Laboratory 8, Calorimetry, Specific Heat, and Energy in Foods. Okay, so let's talk a little bit about the procedure now. So let's look at part A, focusing on temperature. So in Canvas, you're provided a set of photos where the temperature was measured for room temperature water, ice water, and ice water saturated with salt. You'll record the temperature for each of these samples in Celsius, and then you'll convert the temperatures from Celsius to Fahrenheit and Kelvins. You're going to want to need to have your calculator handy and available for this, as these calculations require the use of a calculator in most cases. So here's the procedure. We're going to view the photo in Canvas. We'll record the temperature of the room temperature water in Celsius. We're going to view the photo in Canvas. We'll record the temperature of the ice water in Celsius. And then we're going to view the third photo and record the temperature of the ice water saturated with salt. Once we have all of these measurements taken in Celsius, we'll convert the temperatures in Celsius to Kelvin using the following equation. And then we'll convert the temperatures in Celsius to Fahrenheit using the following equation. Okay, so let's take some measurements. So here's the room temperature water we see in our thermometer. It's about 23.4 degrees Celsius. Okay. Let's now take the temperature of the ice water, which is about 0.4 degrees Celsius. Finally, we have the ice water saturated with salt. Generally, when you dissolve salt in water, this lowers the freezing point of the sample. So generally, if you want to prepare a sample of ice water at a lower temperature, you mix in a large quantity of salt. That in turn lowers the freezing point, which allows you to get a lower temperature sample of ice water. So in this case, our temperature of the ice water that's been saturated with salt is negative 4.1 degrees Celsius. Okay, so now that we have that taken care of, you're going to do the temperature conversions to Kelvin and Fahrenheit independently now that you have these initial temperature readings. Okay, that's the first part, temperature. Now let's talk about part B, specific heat. In this case, we are determining the specific heat of a metal sample across 3 trials. We're going to be figuring out and determining the specific heat of the metal sample using a method known as calorimetry, where we record changes in temperature and use that in order to calculate the specific heat of our sample. So in this case, we're going to be watching a video where the specific heat was measured for a sample across 3 trials. You're going to view the video and record the mass of metal. You're then going to record the mass of water added to the styrofoam cup calorimeter for each trial. You're going to record the initial temperature of water in the calorimeter each trial. During the video, we're going to heat the metal sample using a boiling water bath. The temperature of the boiling water bath is going to be consistent across all of the trials. So when we measure the temperature of the boiling water bath, you're going to want to record that temperature. So you're going to record the temperature of the boiling water, which is the same as the temperature of the heated metal piece, and you're going to use that value for all 3 trials. You're going to want to observe the calorimeter as the heavy metal piece, as the heated metal piece is transferred from the boiling water bath into the calorimeter. What we're doing is allowing the metal piece to exchange heat with the water in the calorimeter, and as a result, the temperature of the water in the calorimeter is going to increase and change. By measuring this change in temperature of the water in the calorimeter, we can figure out how much heat was exchanged between the water and the heated metal piece that we added to the water. And based on the mass of the metal piece and the temperature data, we can figure out the specific heat of our metal sample. So, what is the video showcasing? The video showcases the following experimental procedure. A styrofoam cup calorimeter is assembled and weighed. The calorimeter is essentially an insulated system that minimizes heat exchange with the surroundings. We're going to place about 50 mils of water into the calorimeter, and we're going to weigh the amount of water in the calorimeter. A metal piece is then weighed, and we're going to record the mass of the metal piece. We're then going to take that metal piece and we're going to heat it in a boiling water bath. We're going to make sure to measure the temperature of the boiling water bath, which is going to be the same as the heated metal piece because they're going to be at thermal equilibrium. They're at the same temperature. Once we have the metal piece heated thoroughly, we're going to place a thermometer into our calorimeter and record the temperature of the water inside the calorimeter. We're then going to transfer the metal piece into the calorimeter and record the temperature over time. The temperature is going to increase and we're going to stir the sample to ensure efficient heat exchange, and we're going to record the temperature over 5 to 10 minutes. Once the highest temperature is observed, we're going to record the highest final temperature of the calorimeter, metal, and water inside the calorimeter. These are all going to be at the same final temperature. This procedure is repeated 2 times for a total of 3 trials, and the specific heat is calculated from the collected mass and temperature data. I know that's a lot to take in, but let's just break it down into the component pieces. So what are we doing? So here's our virtual lab procedure. We're going to view the video in Canvas. So here's the video. This is the part B laboratory, and let's make sure we know what we're keeping our eye out for. We're going to make sure to record the mass of water for trial 1. We're going to observe the metal piece in the video, and we're going to record the mass of metal. we're going to use the same metal mass for all three trials. The mass of metal is not going to change. We're going to observe the water inside the calorimeter, and we're going to record the initial temperature of water inside the calorimeter, which is the styrofoam coffee cup. We're going to observe the metal piece as it's heated. And when it's measured in the video, we're going to record the temperature of the boiling water and the metal piece when it's measured. I'll show you when that is. You're going to use the same temperature of boiling water and the heated metal piece for all three trials. You're going to carefully observe what happens when the heated metal piece is transferred to the boiling water bath and into the calorimeter. We're going to observe how the temperature inside the calorimeter increases after we added the heated metal piece to it. You're going to record the highest final temperature observed for the water, metal, and calorimeter for trial 1. We're going to repeat this process for a second and third trial and record the same data for the second and third trials. Okay, so here's our data table. We're going to watch the video carefully, and we're going to make sure to record the mass and temperature data. Okay, so here is the setup. So first and foremost, we need to prepare our coffee cup calorimeter. So we have a balance set up. So first and foremost, I'm setting up a weigh boat, and I'm adding a metal piece to the weigh boat. We're going to carefully record the mass of the metal piece, which is 9.9 grams. This is a piece of aluminum, by the way. So we're going to use the same mass of metal piece for all three trials. Okay. So we've weighed out our metal piece. We've recorded the mass. And I would encourage you to watch the video in full with narration, but I'm going to be providing some narration as part of this real-time walkthrough. So here I prepared a coffee cup calorimeter, which is 2 styrofoam cups. This is a surprisingly useful tool for calorimetry experiments that works quite well and can allow us to calculate reasonably accurate specific heat values. So now I'm going to place my coffee cup calorimeter on the balance and put the top onto it, and I'm going to tare it. This in turn means that any water we add to it, we can just weigh it directly on the balance without having to do any subtraction operations. The balance is already doing that for us. Okay, we're now going to prep the water. So I have some distilled water that I've already prepared in a separate video. The preparation of the distilled water is not super important. Okay, so I've dispensed some distilled water and I'm transferring that into my coffee cup calorimeter. Okay, so I've transferred the water. I don't need to care as much about the volume of water because I'm weighing it, and the mass of water is what's most important, is that's what we're going to be using for heat calculations. So our mass of water is 48.3 grams for trial 1. Okay. Remember, we're going to use different masses of water for each trial just because we have to clean out the calorimeter each time. Okay, let's keep going now. So we have the coffee cup calorimeter prepared. I have my metal piece prepared. And now we're going to get ready to heat the metal piece in a boiling water bath. For those curious, this lab is also done as part of home laboratory box kits. Um, so in this case, we're showcasing the heating of the metal piece. This is a classic home chemistry procedure, and you can get surprisingly accurate data from it. So we have our metal piece, and we're going to heat it in a boiling water bath. So I've set some water to boil, and we're heating the metal piece. We're going to let that metal piece sit in the boiling water bath for about 10 to 15 minutes. While we're doing that, I placed a thermometer into the calorimeter, and we were able to take a reading for the temperature of the water inside the calorimeter, which was 21.6 Celsius. Okay, let's keep watching the video. So now we have our heated metal piece. We have our calorimeter ready to receive the heated metal piece. And we're going to transfer the heated metal piece into our coffee cup calorimeter. We're then going to cap the coffee cup calorimeter and we're going to stir it and we're going to monitor the temperature over time. So the heated metal piece is transferring heat into the water in the calorimeter. And as we can already see, the temperature is starting to increase. So we see it's at 23.3 Celsius now. Now, we're going to let the sample sit and we're going to stir it thoroughly. And I'm going to keep monitoring the temperature. As you can see, this calorimeter is doing a pretty good job of keeping the temperature pretty consistent as the temperature hasn't dropped due to heat exchange with the surroundings. So now I'm agitating and mixing the water in the calorimeter to try to get some heat exchange to occur. And now we're letting it sit. It's still at 23.3 degrees Celsius. Still at 23.3 degrees Celsius. Just sort of waiting. And as you can see, the temperature has now increased slightly to about 23.5 degrees Celsius. Okay, so this is when the temperature has finally stabilized. So let me go back to that. So here is the highest temperature we were able to record across 10 to 15 minutes of mixing. So 23.5 degrees Celsius. So this is the final temperature that we observed for the water and metal in the calorimeter. For those wondering where are we going to get the temperature of the boiling water and heated metal piece, we'll be able to get that from the video in one moment. Okay, so now, once again, I'm going to prep a new coffee cup calorimeter. I've emptied out my coffee cup calorimeter, and now we're going to prep a new set of water to fill in the coffee cup calorimeter. So I'm emptying out the old water that I used, taking out the metal piece, and now we're going to reweigh a new batch of water. Okay, so I've tared my coffee cup calorimeter and I've tared it with the cap. And now I'm going to add a new batch of water. Again, we're adding about 50 milliliters of water. So we're going to get a mass anywhere between 48 and 50 grams of water, just based on the density. Okay, so we added the water to our calorimeter for the second trial. The reason why we do multiple trials is just for consistency. Okay, now let's record the mass. This gives us a mass of 53.4 grams of water for trial 2. Okay, we're now ready to go to move on to heating the metal piece and running our second heating trial. Okay, so we have the coffee cup calorimeter, metal piece, and our heating setup. Here is the initial temperature of the water inside the calorimeter, 22.2 degrees Celsius. Okay, we're now ready to start the process of heating the metal piece and recording the temperature of the boiling water bath. So I'm recording the temperature of the boiling water bath using my digital thermometer. As you notice, we're going to wait for this temperature to settle before we record a temperature reading. Okay, it looks like it's leveled out at 96.8 degrees Celsius. Okay, it's finally settled down. Give it a few moments. Let's go back. So it finally settled at 97.1 degrees Celsius. It's important to allow the temperature to equilibrate to get the best temperature reading. So we're going to use this temperature of the boiling water for all 3 trials. And because the metal piece has been sitting in the boiling water for a long amount of time, they should be at the same temperature. Okay, we're now ready to transfer our metal piece and take some temperature readings. Okay, so we have the metal piece. We're going to add the metal piece to the boiling water bath, and we're going to let it heat for about 10 to 15 minutes. In the meantime, we're setting up our coffee cup calorimeter. One moment. So we took the metal piece and we heated the metal piece in the boiling water bath. We're now ready to transfer that metal piece. So the metal piece has been heating in the boiling water bath. We're going to let it continue to heat in the boiling water bath. We have our coffee cup calorimeter. Gonna get that calorimeter set up. So right now we're just waiting for the metal piece to heat up and reach target temperature. We're now transferring the metal piece. Let's just show that once again. So we have our coffee cup calorimeter ready to go. We then transferred the heated metal piece into the coffee cup calorimeter once again, and we're going to start recording the temperature. So as you watch the video, we're transferring the metal piece into the coffee cup calorimeter. The metal piece that's been heated goes into the calorimeter. And now we're going to record the change in temperature over time. So we're going to cap our calorimeter and start recording the temperature. So our temperature has already increased to 24 degrees Celsius. We're going to let the water and the heated metal piece mix and exchange heat with one another over about 5 to 10 minutes, and we're going to monitor the temperature each time. So as we notice, the temperature is starting to drop, but we're still going to keep monitoring the temperature as heat's exchanged between the metal piece and the water. So we're allowing time to pass, letting the metal piece and water exchange heat, and that gives us a final temperature of about 23.8 degrees Celsius. So we'll record that as the final consistent temperature. Okay, so we've finished our temperature readings for trial 2. In this case, after a little bit more time, the temperature has increased slightly to 24.0. So we're going to revise our temperature reading to 24.0. Sometimes the heat exchange takes a little bit of time. Okay, so that's pretty much set for trial 2. Temperature is still at 24.0, holding consistently. So that concludes our trial 2. We're now ready to set up our calorimeter for trial 3. So we're going to clear out the water, transfer out the metal piece, and get things ready for our third trial. So again, we're tearing our coffee cup calorimeter, and we're adding our third batch of water to it. So we've transferred the water into the coffee cup calorimeter, and this has been pre-taired already. And this time we have a mass of water of 50.0 grams. So let's record that. Okay, we're now ready to begin heating the metal piece and that transfer process. So we're loading up the coffee cup calorimeter, and then we're going to walk it over to our heating station. So here's our station. We're now going to record the initial temperature of the water inside the calorimeter. We're going to give it a few moments to reach a stable temperature. And this gives us a temperature of initially of the water in the calorimeter for our third trial is 22.7 Celsius. So let's record that. Okay, we're now ready to start heating the metal piece. So I'm taking the metal piece and heating it again in the boiling water bath. We're going to let that metal piece heat in the boiling water bath for about 10 minutes. So let's now begin the process of transferring the metal piece over. So we've transferred the heated metal piece into our calorimeter. We're now going to put the cap onto the calorimeter and put the thermometer in. And we're going to record the change in temperature of the water inside the calorimeter over time. So taking a look at the thermometer just initially, the temperature is already starting to increase. We've observed a temperature of 24.2 degrees Celsius. We're going to let the water and the heated metal piece mix and exchange heat for a little bit more time, and then we'll record our final temperature. So the temperature is still sitting pretty clearly at 24.2. We're going to give it a little bit more time. The temperature has dropped to 24.1. So that tells us 24.2 was our peak temperature. So let's write down our highest temperature observed, which was 24.2 degrees Celsius. Okay, so as you can see, the temperature hasn't increased further as time is passing. This is just more time passing where we've allowed the water and metal piece to exchange heat. The temperature is still less than 24.2. It hasn't increased. So we've recorded our highest observed temperature. Okay, so we've collected all of the mass and temperature data. Let's now process this data. So in this case, we're going to calculate the change in temperature of the water inside the calorimeter by taking the difference between the final temperature and the initial temperature of the water in the calorimeter. We're going to calculate the heat gained by the water sample by taking the mass of water times the specific heat of water, which is 4.184 joules per gram degree Celsius, times the change in temperature of the water in the calorimeter. As any heat gained by the water is lost by the metal, the heat lost by the metal is equal to the heat gained by the water times -1. We're then going to calculate the change in temperature of the metal piece by taking the difference between the final temperature of the metal in the calorimeter minus the temperature of the heated metal piece, which is the same as the boiling water. From there, we'll be able to calculate the specific heat of the metal by taking the heat lost by the metal divided by the mass of the metal times the change in temperature of the metal. Okay, so let's do some calculations here, and I will do them for the first two trials, and I will do them for the first trial, and you'll do the remaining calculations for the remaining trials. So let's transplant that data over, and let's go through it step by step. I'm just taking the data that I've collected and moving it down. Okay, so here's our data For the mass of water, we have the mass of the metal. This is the temperature of the metal, which is the temperature of the boiling water bath. This is the temperature initial of the water, and this is the temperature final of the water plus the metal. Okay, so let's now execute on our calculations. Let's now execute on our calculations here. So in this case, if we want to calculate the delta T of water, we just take T final minus T initial. So first, delta T water is equal to T final minus T initial. Okay, so the final temperature of the water for trial 1 is 23.5 degrees Celsius. The initial temperature was 21.6 degrees Celsius. This gives us a delta T of water. Let's break out the calculator. So we have 23.5 minus 21.6. This gives us 1.9 degrees Celsius. Okay, so far so good. Next, we're going to calculate the heat gained by the water by taking the mass of water times the specific heat times the change in temperature. Okay. Q water is equal to mc delta T. In other words, Q water is equal to the mass of water, which is 48.3 grams, times 4.184 joule per gram degrees Celsius. This is the specific heat, and our delta T of water was 1.9 degrees Celsius. This gives us a Q water equal to 383.96 joules, because grams and degrees Celsius cancel. And we know that Q metal is equal to negative Q water, which would be negative 383.96 joules. In practice, we'd round this answer to 380 joules, but we're not going to round till the end when we're doing this calculation series to avoid introducing rounding error. Okay, so we calculated the Q metal, which is negative Q water. We're now going to calculate the delta T metal, which is the final temperature of the metal in the calorimeter minus the temperature of the boiling water and metal piece. So we have delta T metal, which is equal to T final minus T initial. The final temperature of the water and metal for trial 1 is 23.5 degrees Celsius. We got that from up here. The initial temperature of the metal is right here. It's 97.1 degrees Celsius. This is going to be a negative number, and that's normal. This is telling us that the metal has decreased in temperature compared to when it started, which makes sense. We took metal that was sitting boiling water and transferred it to metal at room temperature. The metal has cooled down as it transferred heat to the water. Okay, now that we have the delta T metal, what we're going to do is we're going to solve for the specific heat by taking the heat lost by the metal divided by the mass of metal times the change in temperature of the metal. Okay, so C metal is equal to Q over M delta T. We know Q metal is negative 383.96 joules. The mass of metal is 9.9 grams, and the change in temperature of the metal was negative 73.6 degrees Celsius. So punching this into our calculator, we see the negative signs cancel. That's good. Specific heat is always a positive number. So we're going to divide by 9.9. And then we're going to divide by 73.6. And this gives us a specific heat of 0.5269 joule per gram degree Celsius that we in turn round to 0.53 joule per gram degree Celsius. Okay, so with that, we've calculated the specific heat of our metal, which will now enter into our table for trial one. So the delta T water that we calculated was 1.9 degrees Celsius. The Q water was 380 joules. The Q metal was negative 380 joules. The delta T of the metal was negative 73.6 degrees Celsius. The mass of metal was just 9.9 grams. And the specific heat of the metal that we calculated was 0.53 joule per gram degrees Celsius. I did all of these calculations for trial one. I want to see you include the final values for trial two and trial three in your final report. So you'll do the calculations for trial two and trial three on your own. I've shown you the example calculation for trial one. You'll use the data for trials two and three to do the same calculations for trials two and three. You're also going to answer the post-lab questions where the metal sample is aluminum and its actual specific heat is closer to 0.897 joule per gram degree Celsius. And it's asking, how does your measured specific heat compare to the literature value? It's not uncommon when we're measuring specific heats experimentally for there to be some variance between the experimental and true value, because with the equipment we're using, it's very easy for heat to be lost to the surroundings. Okay, let's move on to the next part, energy in foods. So if you look at a food label, you often see that the labels have certain calorie values. So this is essentially a measure of how much energy that food sample can provide, where if you were to eat the food sample, how much energy does that food sample have that can be used for biological reactions and other purposes. Um, what's happening is that food sample has chemical bonds, and by taking that food sample and reacting it, we can produce energy. We're going to measure the energy in a food sample by just burning it and measuring the heat generated as we burn that food sample. So in Canvas, you're provided a video where the energy of combustion for a food sample is measured. You're going to view the video and you're going to record the mass of the food sample and the holding stand weighed. You're also going to record the mass of the metal cup calorimeter. You're then going to record the mass of water added to the metal cup calorimeter and the initial temperature of water in the calorimeter. The food sample is going to be burned in the video, and that burning of the food sample is going to be used to heat the water inside the calorimeter. You're going to observe the food sample as it burns and observe how the temperature of the water in the calorimeter changes over time. You're going to record the highest temperature observed for the water inside the calorimeter after about 5 to 10 minutes. Importantly, because we can't completely burn the food sample, to determine how much food sample we burned in this process, we're going to record the final mass of the burned food sample and the holding stand. From the mass and temperature data, the caloric energy in joules per gram of the food sample can be calculated. So this video provides a showcase of the experimental procedure in which a metal cup calorimeter is assembled and weighed. 30 mils of water is added to the calorimeter, and the mass of water in the calorimeter is measured via weighing. A food sample holder is assembled and weighed. A food sample is placed in the sample holder, and the combined mass of the food sample and the sample holder is weighed. A thermometer is then placed into the calorimeter, and the temperature of the water inside the calorimeter is recorded. The food sample is then placed under the calorimeter and burned. The sample is stirred, and we record the temperature as it increases over time. Once the highest temperature is observed, we're going to write down the highest final temperature of water in the calorimeter. The final mass of the burned food sample and sample holder is then recorded. Okay, I know that's a lot to take in. Let's break it down into our step-by-step procedure. We're going to view the video in Canvas. You're going to record the mass of the food sample holder. You're going to observe the food sample and record the combined total mass of the food sample and the sample holder. You're going to observe the metal calorimeter and record the mass of the empty calorimeter. You're going to observe as water is added to the calorimeter, and you're going to record the mass of the calorimeter in water. We're then going to observe the water in the calorimeter and record the initial temperature. You're going to watch carefully as the food sample is burned, and we're going to record the highest final temperature observed for the water as the food sample is burned. Finally, we're going to note the appearance of the food sample after it was burned, and we're going to record the final mass of the food sample and sample holder after the food sample is burned. So let's go to part C and let's take a look at the video. So this is the Energy and Foods Calorimetry Lab. So we have our sample holder, our metal calorimeter cup, some water, and a temperature probe. The food sample that we're burning is just a peanut. They burn quite well. So we're going to load it onto the sample holder. You can't just burn it on the lab bench. The sample holder allows us to take consistent mass readings. Okay. Okay. So first and foremost, they are tearing the balance and they're recording the combined mass of the food sample and the sample holder, which is 10.0 grams. Okay, so let's write that down. So the mass of the food and sample holder is 10.0 grams. We're going to leave the mass of the sample holder blank for now. They've already tared it. Okay. They're now going to set up their calorimeter and load it with some water. So first, they're going to weigh the calorimeter. So here's the mass of the empty calorimeter, 30.8 grams. So let's write that down. We're then going to add some water to our calorimeter. And then we're going to weigh it once again. This gives us a mass of 82.3 grams. Let's write that down. So we added about 50 mils of water. Okay. Now for what I would consider the fun part. I'm going to set up the calorimeter in and prepare it for heating. We've set up the temperature probe that's in the water inside the calorimeter. And we have our initial temperature reading for the water inside the calorimeter of 21.2 Celsius. Okay, now we're ready to burn the food sample. So the food sample is going to be placed under the calorimeter and then burned. So here we go. The food sample is placed under the calorimeter, and now we're going to burn that food sample. So as the food sample is burned, it's going to be releasing heat into the surroundings as we're converting the various compounds found in the food sample into carbon dioxide, water, and other byproducts. Burning the food sample releases heat. That heat gets transferred to the water in the calorimeter, and the water in the calorimeter heats up. As you notice, the temperature of the water has increased already to about 27 Celsius. So we're going to continue to burn the food sample. After the food sample has finished burning, this is the final temperature of the water inside the calorimeter. So it's increased to almost 40 Celsius, which is quite remarkable. So let's write that down. 39.8 Celsius is the final temperature. But we aren't done. We need to figure out how much food sample did we actually burn. So they're going to weigh the burned food sample in the sample holder. And we have a final mass of 9.7 grams. So let's write that down. Once again, let's take a view of that. 9.7. Okay, so let's write that down. Okay, we have all the data that we need. Now let's go to the calculations. So we're going to calculate the mass of water in the calorimeter by taking the difference between the mass of water in calorimeter minus the mass of the empty calorimeter. We're going to calculate the change in temperature of the water inside the calorimeter by taking T final minus T initial. We're going to calculate the heat gained by the water sample by using the mass of water times the specific heat times the change in temperature for the water sample. Because any heat gained by the water is lost or released by the food sample, we can calculate the heat released by the food sample by taking the heat absorbed by the water times -1. To calculate the mass of food burned, we're going to take the mass of the food and sample holder minus the final mass of the burned food and sample holder. The change in mass is how much food sample was burned and reacted. We're then going to calculate the energy in joule per gram of the food sample by taking the heat released by the food sample divided by the mass of food burned. Okay, so those are our marching orders. So let's first just sort of copy and paste our data over. Okay. Okay. So this is the mass of the calorimeter. This is the mass of the calorimeter plus water. This is the mass of the food plus the holder. This is the T initial of water. This is the T final of water. And this is the mass of the burned food plus the holder. Okay, so let's follow through the calculation step by step. We're going to calculate the mass of water by taking the mass of water in the calorimeter minus the mass of the empty calorimeter. Okay, so let's do just that. The mass of water is the mass of the water plus the calorimeter minus the mass of the empty calorimeter. Okay, so we have 82.3 minus 30.8. That in turn gives us 51.5 grams. Okay, let's do the next part. We're going to calculate the change in temperature of the water by taking the final temperature of water minus the initial temperature. So delta T water is equal to T final minus T initial. So we have 39.8 degrees Celsius minus 21.2. That in turn gives us 18.6 degrees Celsius. We're then going to calculate the heat gained by the water sample by taking the mass times the specific heat times the change in temperature. So Q water is equal to mc delta T, where C is 4.184 joule per gram degree Celsius for water. This is found in both the lab manual and the pre-lab lecture. So we have 51.5 grams of water times 4.184 joule per gram degrees Celsius times 18.6 degrees Celsius. This gives us a Q water of 4,007.8536 joules. We'll round at the end. In this case, because our inputs have three significant figures, this would be 410, 4,010 joules rounded, which we can also write as 4.01 times 10 to the third joules. Okay, now let's calculate the heat released by the food sample, which is the same as the heat gained by the water sample. So Q food is equal to negative Q water, which would be negative 4,007.8536 joules. Okay, let's now calculate the mass of the food burned by taking the mass of the food in sample holder minus the final mass of the burned food in sample holder. So to calculate the mass of the food sample, we take our initial mass, which is 10.0 grams, minus the mass of the burned food sample in sample holder, which gives us 0.3 grams. Finally, to calculate the energy in joules per gram, we take the heat released by the food sample divided by the mass of food sample burned. So in terms of that, let's calculate that. So Q food over M food is equal to 4,007.8536 joules over 0.3 grams. That in turn gives us 13,359.5 joules, which we round to 13,000 joules. If we know that in 1 kilojoule there are 10 to the third joules, this is in turn 13,000 joule per gram. We can write it as 13 kilojoule per gram. Okay, so with that, we've completed our calculations in terms of figuring out the amount of energy released as the food sample is burned. Okay, so let's fill in the table. The mass of water is 51.5 grams. The delta T of water is 18.6 degrees Celsius. The Q water is 4,010 joules. The Q food is 4,010 joules. Negative because heat's released. The mass of food burned is 0.3 grams. And the energy of the food sample in joule per gram is 13,000 joules per gram, which in turn is equivalent to 13 kilojoules per gram of food sample burned. Wonderful. So with that, we've completed the calculations for this part of the lab. There's one more thing that we have to do, which is the energy and food section. So in Canvas, you're provided a food sample's nutritional label. And here you're going to calculate the energy from carbohydrates, fats, and proteins in the food sample. Nutritionists estimate that of the three food types, carbohydrates have a value of 17 kilojoules per gram, fats have a value of 38 kilojoules per gram, and proteins have a value of 17 kilojoules per gram. For example, a candy that has 12 grams of carbohydrates provides about 204 kilojoules of energy. So let's view the photo in Canvas and let's do some calculations. So here's the photo. This is, I believe, like a can of beans. And let's take a look at the contents. So this is a sample of beans. Its serving size is 130 grams. The grams of fat in one serving, I see 0. Protein, I see 7 grams of protein, and carbohydrates are 21 grams. So let's note that. So 0 grams, 0 cal. For the grams of carbohydrates, it was 21 grams. From the calories, if we have 21 grams for carbohydrates, there's 17 kilojoule per gram. 21 times 17 gives us 357 kilojoules that we round to two significant digits, or 360 kilojoules. In terms of protein, we have 7 grams of protein. So in terms of calories, 7 grams times 17 kilojoules per gram. This gives us 119 kilojoules that we round to 120 kilojoules. So in total, in one serving, in terms of the total calories in one serving, if we're looking at the kilojoules, we have a total in terms of kilojoules as 480 kilojoules. And we can go 480 kilojoules times, in this case, 1 kilocal for 4 kilojoules, which gives us about 120 kilocal. We can also do these calculations in terms of calories. So if we have 21 grams and we want to calculate in terms of calories, carbohydrates are 4 kcal per gram, which would give us 48 kilocalories. And then for proteins, if we have 7 grams times 4 kcal per gram, this in turn gives us 28 kcal. If we add up 48 plus 28, that in turn gives us about 76 kcal. So two methods, both are more than fine. Note that the caloric estimates are often a little bit variable, and these values of 17 kilojoules per gram are not super precise. But as you can see from our calculations, we noted that the calories per serving were about 120 kcal. And if we check the label, the calories per serving matches up with that at about 110. So this estimation is reasonably accurate. Okay, so that concludes our calculations in terms of the energy in a food sample and calculating the caloric value in a food sample. I'd like you to answer the post-lab questions before you complete this full report. So once you've completed each part of your lab report, you're going to be submitting it into the Laboratory 8 report submission page. In this page, when you open the assignment, you'll take either your photos or a Word or PDF document, and you'd upload that file into the following upload link. So that concludes our run through of Laboratory 8, and we'll discuss the next labs in a future video.